Basic Calculus, Lesson 3.1, Derivative of a Function. So this feels like a repeat of what we just did, only now we call it a derivative, and that is actually fairly on purpose. We want to make sure we're clear on where the derivative comes from as a limit as we get closer and closer to the instantaneous slope on a line. So hopefully this looks somewhat familiar. And what I just said, another way to describe the derivative is the slope at a point on the curve. Or more simply, we call this the tangent line. So, a little bit of nonsense here. Be aware of it. I put it in my notes, so it's important, but it doesn't pop up that often. The domain of the derivative may be smaller than the domain of the function, as in the derivative may not exist in a few spots. We'll get to this. But some functions are completely differentiable, like a nice polynomial, x to the third, for example. We say that is a differentiable function, but more on this later. We can spend a whole lesson on it. So the limit as h approaches 0 x plus h to the third minus x to the third over h. There are a few tricks you need to learn when you're doing these problems. Polynomials are not that hard. They kind of handle themselves. I've done this often enough that I know what's coming. Apparently not. If you FOIL out that 3 times, distribute it out 3 times, this is what you'll get. I don't need these parentheses anymore. But one of the things I often forget is to rewrite my limit. If you look at this, you'll notice you can cancel these. And then if you look again, you'll notice I can cancel this h, this h, this h, this h. And this is the kind of trick you'll see. Hopefully you remember it from the last unit. I still haven't taken the limit, so I've got to rewrite this whole thing. 3x squared plus 3xh plus h squared. Well, as we put it to 0, this is going to be gone, and we get 3x squared. So, great, we just took our first actual derivative. Wonderful. What do we call it? If we have f of x equals x to the third, how do we write the derivative? Lots of ways. This all goes back to Newton in England and Leibniz in what would be modern-day Germany. They just represented it differently, and it really sounds to me like there's a big turf war going on, or has been a big turf war going on. Like, no, Newton found it. No, Leibniz found it, between scholars of different ethnicities. So they do it different ways. That's one way. That's actually Newton's way. Leibniz did it like this. He said dx of f of x equals 3x squared. Or if we had said y equals 3x squared, we could write it as y prime, y equals x to the third. Y prime is 3x squared dy dx equals 3x squared. Things like that. You'll get it. It's not hard. And purposely, I've noticed the AP curriculum do all it can to change them up, just to see if you're on your toes. And again, you just get used to it. It's not a big deal. We're going to do it again where this is one of the other tricks. Instead of getting the function, we'll get it at a value. If the value is given, put the value in. Since it's a, we have to do this. Limit as x approaches a, not as h approaches 0. And we put x in originally, x plus, excuse me, minus square root of a. It's embarrassingly bad square root. Over x minus a. Notice we couldn't put that in. It wouldn't work. So here's another trick you have to get used to. Radicals. I seem to remember something about a conjugate or something. And when I had to redo these and relearn them, I just said conjugate. Let me see where that takes me. Hey, look at that. It worked. X minus a on top over x minus a on the bottom. I find it ironic that we've taught you how to get conjugates off the bottom, but in this case we do the opposite. We reintroduce one back, but we can take the limit now. Get 1 over 2 root a, because we sub into a for x, and there's 2 of them, and we can do that. It works. So we'll get the same answer either way. If we had just done this with the previous technique and then plugged in a at the end, you get the same answer. I like to do the function technique and then plug in my value at the end, because then I have the function. If some jerk math teacher said, okay, now put in a different value for a, you'd be good to go. So anyway, I might have mentioned that the graph is a slope. So here we go. Here is the function. Here is the derivative. And we're introducing this. You're going to actually get really good at this, moving between one graph and the other. So the question you have to ask is, what's the tangent right here? Down there at 2. You'd say, well, the slope of the tangent is 0, so that's why we have a 0 here. The slope here at 6 is also 0. So that's why the derivative graph shows a value of 0. The slope here is negative. It's going downhill. Less so, more so, less so. So everything in here is negative. The slope here is positive. It's up to the right. So everything up here is positive. The slope here is becoming positive again, up to the right. This takes some getting used to, but we'll get there. So I do 2 graphs. Here is the derivative graph. And it's x minus 1, absolute value of x minus 1 over x minus 1. So it's actually going to come out here to 1. Not defined at 1, of course. And then it's going to bounce down to negative 1. And of course I got it backwards. So let's think for a minute. We put in 2, get a positive value out. So yeah, it'll always be 1. Put in 0, you get 1 on top and negative 1 on the bottom. So it'll always be negative. So this is the graph of the derivative. So it tells us that the slope here is 1 and the slope here is negative 1. So that makes it easy to graph the function, except we can put slopes anywhere. So we give you a point This is the function, and at f of 0, it's 0. So it's here. I don't know what that means. So we're to the left side. The slope is -1, so it should be down to the right. Down 1 over 1. It's open here. There's no slope defined at 1. I gotta think about that. Oh, it's continuous, so can't have a gap. So one of them is fine, one of them is not. It doesn't really matter. We're just sketching a graph. And then the slope to the right of that is 1, so up 1 over 1. So if I had to draw this, I would say this is the function. Yeah, something like that. So, more practice, you'll get that. That's tricky to get that. We can also graph a derivative using data, and that's kind of cool, actually. But it's very time consuming. This is why God invented Excel spreadsheets. But what's the probability that two people in a room share the same birthday? That's a silly example, but there it is. So you're in a room with 30 people. Believe it or not, there's a 71% chance almost that two of you have the same birthday. So we'll try this in class and see how we do. We should have a 2 out of 3 chance that somebody has the same birthday, which is weird. And then this is the slope. And what we did was we took these values, went change in y of the probability is 0.117. It's minus 0, so I'm not even writing that in, over 10 minus 0. We got that value, we put it here. And the x point is halfway between the x's, so 10 minus 0 over 2, 5. And then we did it again, and again, and again. And it is tricky. It takes some getting used to. So what do the graphs look like, and what do they mean? Well, the graph of the probability looks something like this. If you plot the points, 0 probability, and then it gets more and more and more closer to a 1 value. Out here at infinity, it'll actually, after you get past 365, you're definitely going to have a 1 because somebody has to have a repeat birthday in there. And the graph of the derivative looks something like this. Peek it out here around 20 or so. So what does it mean? Well, the graph itself doesn't really mean anything. It just shows you what the probability is. And the graph of the derivative shows you that up until about 20 people, every person you add makes a big difference. The slope there is very steep, but the change becomes less and less steep as you get past 20. So, you know, somebody says, oh, I think it's going to go up a lot from person 55 to person 56. No, it's not. The probability, improvement of probability maxed out at 20, and after that, the odds are barely changing. So once you get past a certain number, it doesn't help to have more people in a room. It's a horrible example, but you'll get a chance to play with that. And last but not least, we talk about one-sided derivatives, which really is annoying. It writes out just like the limits we've done before. Limit as h approaches 0 from the negative side, so that means I'm working here, is x plus h squared minus x squared over h is x squared plus 2xh plus h squared minus x squared all over h. Cancel, 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 cancel. It is 2x, and at 0, it's 0. This is an example of me doing it, doing the function, then plugging in the value that they gave me later. So what about on the left-hand side? The limit as h approaches, on the right-hand side. On the positive side, you got to watch this. This is tricky. We've got 2x plus h minus, I'm going to write it in, f of 0. Put in my x here. This time I'm not doing it as a function. This time I am plugging in the value. How come? You'll see. What's f of 0? You say, well, we're working on the right-hand side. No. We are working on the right-hand side for the function here, but when we talk about what f of 0 is, we have to go back to what the original function says. In this case, it's 0, so it's not that big a deal. We get 0 plus h minus, plugging in 0, 0 all over h, 2h. Cancel, and we get 2. So that's a bit annoying. It's not an easy thing to do. It takes some getting used to. But the bottom line is the left and the right hand derivatives are different. So we know that the derivative does not exist. It has to be the same for both sides. More on that in the next lesson. That's it. Happy mathing.